Welcome back to today's Explainer, covering Lesson 4 of our GD&T Master Course material. Today, we're diving into the absolute bedrock of geometric dimensioning and tolerancing. We're talking datums, datum features, and datum simulators. If you want to design parts that actually work in the real world or inspect them without pulling your hair out, you've got to understand these ASME standard concepts. So, let's just jump right in.
Imagine a freshly machined bracket just came off the line. It looks great. You hand it to 3 different quality inspectors. Inspector A measures it and gives it a thumbs up, pass. Inspector B slaps a rejection sticker on it, says it's totally out of tolerance. Then Inspector C measures it and gets a completely different set of numbers entirely? Cue the massive shouting match on the manufacturing floor, right? How does this even happen with the exact same piece of metal? Well, it's because each person referenced the part differently during their setup. They oriented it using completely different surfaces. And honestly, this perfectly illustrates why we absolutely need a common, undeniable reference system. Because without one, you're literally just guessing.
To sort this all out, we're going to hit 5 key areas today. First, why we need datums. Second, the difference between datums and datum features. Third, simulators and degrees of freedom. Fourth, real-world inspection. And finally, some incredibly common mistakes you'll want to avoid.
All right, Section 1. Why we need datums in the first place.
Datums are exactly what solve our 3-inspector nightmare. They give us a universal, rock-solid coordinate system. By defining datums on your drawing, you're not just throwing lines on paper. You're dictating the actual functional relationships between the features of your part. You're telling the CNC machinist exactly how to fixture that block of metal, and you're telling the quality team exactly how to orient it on the granite table later. When everyone works from the exact same origin point, measurement becomes consistent, it becomes repeatable, and most importantly, it actually reflects how that part is going to function when it's fully assembled.
Moving right along to Section 2, Datums versus Datum Features.
Now this is a crucial distinction. By definition, a datum is a theoretically exact reference. Think of a perfectly flat plane, a perfectly straight axis, or a dead center plane. But here's the catch. It lives entirely in the ideal mathematical world of your 3D CAD model. A true, mathematically perfect datum doesn't actually exist anywhere in the physical universe. You can't touch it, you can't hold it, it is 100% imaginary.
Which brings us to the physical side of things, the datum feature. This is the actual, tangible thing you can hold in your hand. It's that physical machined surface, the drilled hole, the slot on your part. And because it's a real physical object, it is inherently imperfect. It's got form errors, microscopic peaks and valleys, maybe a little warp from heat treatment. So the datum feature is the messy physical reality we touch, while the datum itself is the theoretical perfection we're trying to reference.
You can see exactly how this relationship plays out on a standard drawing callout. Notice how the physical datum features, like the right face or the top face, are what actually get tagged. In reality, those imperfect, slightly wavy physical surfaces are brought into contact with perfect, theoretical datum planes. We interact with the physical part, sure, but the tolerance zones, those are established by those perfectly straight imaginary boundaries.
Let's jump into Section 3, simulators and degrees of freedom.
So how do we bridge that massive gap between perfect theory and imperfect reality? We use datum simulators. Since we obviously can't touch a perfect theoretical plane, we use the absolute closest physical approximation humanly possible. We're talking high-precision, real-world tools. A massive, incredibly flat granite surface plate that acts as a simulator for a planar datum because its sheer mass resists warping and vibrations. A precision ground gauge pin simulates a perfect cylindrical hole. Mandrels, V-blocks, custom inspection fixtures, these are the tangible, real-world tools that mate with your part's imperfect features to establish that actual datum reference frame.
And here's how we physically build that setup. Any free-floating part in space has 6 degrees of freedom. Think of a drone flying around. It can go up and down, left and right, forward and backwards, and it can pitch, yaw, and roll. To machine or measure a part accurately, we literally have to lock all of that down. We do it using a functional hierarchy. First, you mate the part to the primary datum simulator, which usually knocks out 3 degrees of freedom right off the bat. Then you slide it against the secondary datum simulator, arresting 2 more. Finally, you push it against the tertiary datum simulator, locking that very last degree of freedom. This 1-2-3 sequence physically immobilizes the part exactly as it would sit in its real-life assembly.
All right, Section 4, Real-World Inspection Applications.
Modern technology handles this in a really fascinating way. Take a coordinate measuring machine, or a CMM. When that ruby-tipped probe goes in to inspect a part, it's essentially acting as a digital datum simulator. It goes around touching the imperfect physical datum features in multiple spots. Then the computer takes over. The software uses all those physical touchpoints to mathematically calculate the perfectly flat, theoretical planes and axes. It takes the messy physical reality, cleans it up, and translates it right back into our theoretical framework to check the tolerances. Pretty cool, right?
And this is definitely not just some academic textbook exercise. Across massive industries, from the incredibly tight tolerances of aerospace brackets and automotive engine components to churning out millions of ejection-molded housings for consumer electronics, datums are quite literally how we guarantee parts fit together. Think about it. If you're manufacturing 1 million cell phone cases, your datums absolutely must reflect how the circuit board snaps into that plastic housing. Because if they don't, well, you've just manufactured 1 million pieces of highly expensive scrap.
Which leads us perfectly into Section 5, Common Datum Application Mistakes.
Getting this wrong has some pretty severe consequences. The first major pitfall is what we hammered home earlier, confusing the theoretical datum with the physical feature. But look at that second one, treating a rough, non-machine surface as a primary datum. If your primary reference is a bumpy, as-cast surface, your part is just going to rock back and forth on the granite plate. That physical instability will instantly propagate measurement errors through every single other dimension on your drawing. And if you ignore that primary, secondary, tertiary functional hierarchy, your quality team is going to align the part completely wrong, and you'll end up projecting perfectly good parts.
Honestly, talk to any experienced machinist or inspector, and they will rattle off a list of drafting pet peeves. Please, save yourself the headache and avoid these. For one, never pick imaginary points in space as datums. How on earth is an inspector supposed to put a probe on a physical point that literally isn't there? It is a guaranteed way to make enemies in the quality department. Another massive pet peeve, slapping a datum directly on a center line. That leaves everyone completely guessing which physical feature actually establishes that center line in the first place. Keep it simple, guys. Use actual functional surfaces, don't overcomplicate things with unnecessary datums, and always remember that an actual human being has to physically set this part up on a machine.
So, if you remember just one thing from today's explainer, make it this. Proper datum selection is the ultimate translator. It's the functional, reliable bridge between the perfect theoretical geometry in your CAD system and the beautifully imperfect physical parts rolling off the manufacturing floor. When you apply datums correctly, you are guaranteeing that your original design intent actually survives the messy reality of the real world.
Now that we've got a solid grip on datums and simulators, we need to put them together to completely lock down those 6 degrees of freedom. We are going to cover exactly how to do that in our next lesson, datum reference frames and the 3-2-1 positioning principle. But until then, I want to leave you with this thought. If every single physical part we ever manufacture is inherently flawed and imperfect, just how perfect does our math need to be to keep the modern world running? Thanks for joining me for this explainer, and I'll catch you in the next one.